Yes, impregnation. So it consists in forming a mat of cellulose nanofibrils, like nano paper if you want. And then this mat that contains some water can be solvent exchange to a solvent, of course, that can dissolve the polymer that will be used, and then can be impregnated. In this case, it was with a solvent and monomer, so it was a thermoset polymer that was polymerized in situ. Then it was dry and hot press to obtain a composite. Of course, in this case, the cellulose content is quite higher because we start from a mat with a given porosity, and the porosity is filled with the polymer. Extrusion, injection molding, we have seen, are commonly used to process thermoplastic materials, and why not using this to process cellulose nanocomposite? Before that, I have some remarks. CNC versus CMF. Melt processing has been mostly applied to CNC reinforced polymer nanocomposite, which is not really surprising, because you imagine that these very long filaments can be hardly dispersed mechanically in a polymer melt. So melt processing method seems to be trickier to apply to CNF compared to CNC because of the entanglement. So we can consider that nanocrystals are more adapted for melt processing. Second remark regarding the polarity of the matrix. When using a polar matrix, which is the case for polyethylene oxide, for starch also, extrusion can be performed directly with raw cellulose nanoparticles, and we can expect strong interaction because both the matrix and the filler are hydrophilic. An exception to this rule is for polyamides, because their melting point is high, and so it's necessary to protect the cellulose nanoparticles from thermal degradation. But even in the case of a polar matrix, functionalization of the nanoparticle can be implemented, for example, with polyethylene glycol, because it prevents the degradation of the nanoparticles. Remark number 3. PLA, polylactic acid, has been broadly used. So, of course, it's appealing because PLA is considered as a biodegradable polymer, but it is not. It is biocompostable only, and only in industrial compost. I don't like PLA, I have to tell you. I don't like because it is based on food resources, so it is based on corn, and the properties are very poor. So it's a very brittle polymer, and the TG is very low, so it's around 60 degrees. I don't like. Apart from being so biodegradable, derived from renewable resources, so the objective, of course, is to obtain, let's say, fully biodegradable or compostable nanocomposite can be explained by the slow kinetics of crystallization of PLA compared to other polymers. So, meaning that it's necessary to use longer molding cycle, but usually PLA is mostly amorphous with a low modulus at high temperature, and high temperature is not so high, it's above TG, and remember that TG is 60 degrees. At the beginning of the PLA story, people were thinking about coffee cup, and so you imagine the polymer with a TG at 60 degrees, and you drop some hot water inside. It doesn't work very well. Accelerating the kinetics of crystallization of PLA to obtain high crystallinity in a short time, enhancing its high temperature modulus, has been extensively studied. You will see in my slide, mainly I use polyethylene and polypropylene. They have been broadly used. So the reason is that, of course, these polymers are considered as commodity polymers. They are broadly used. And the other thing is that these polymers are highly hydrophobic. So it means that if you succeed in dispersing nanoparticles in this polymer, it can work with any polymer. Remark number 4, compatibilization method. Not surprisingly, physical methods such as preparation of a master batch or physical coating of the nanoparticle with a polymer or surfactant are generally preferred over chemical modification of cellulose nanomaterial. Covalent multifunctionalization normally involves complicated and extensive steps which are difficult to scale up, and so it can be prohibitive for some applications. Now, a comparison between the wet approach that we've seen previously and the polymer melt approach. I report here the advantage and the drawbacks. For the wet approach, the main advantage is that we can preserve the dispersion state of the nanoparticle in the liquid medium, water, but also other liquid medium by different means, by using a surfactant, chemical modification, and so on. The problem is that, of course, there is a limitation in the number of polymer matrices that can be used. And another thing is that this process is non-industrial and non-economic because it generally involves casting evaporation, which is a long process. In the case of polymer melt, it's a green process. I mean by green process that no solvent is involved. Of course, it's an industrial process, so it's economically viable, but you can see that there are several drawbacks. Hydrophilicity. It's necessary to dry the nanoparticles before extrusion. And of course, we can expect aggregation. Then it will be difficult to disperse, to obtain a uniform dispersion of this nanoparticle in the polymer melt. A problem can also be the low thermal stability of cellulose, mainly for cellulose nanocrystals, because we'll see that for cellulose nanocrystals, usually sulfuric acid is used. It is good to have a stable dispersion, but the presence of the sulfate groups decreases the thermal stability of cellulose. Structural integrity of the nanoparticles we'll discuss, and the orientation. So, we'll see each of these drawbacks, and I will show you the possible strategies to avoid these problems. Drying of cellulose nanomaterials. So when water is removed from the suspension, we have an irreversible aggregation, of course, because of the OH group from the surface. Some strategies have been proposed, like, for example, the use of drying techniques that limit aggregation and produce a weakly bond solid material, keeping as much as possible the nano size. Can be freeze drying. So this is a definition of freeze drying, but you probably know. So it's a lyophilization. So it's a low temperature dehydratation process that involves freezing the product and lowering pressure, thereby removing ice by sublimation. So water is sublimated by the direct transition of water from solid to vapor. So there is no liquid state. Spray drying is a method of forming a dry powder from a liquid or slurry by rapidly drying with a hot gas. And there is another one, maybe it's not here, I will report here because I will mention it later. Spray freeze drying, so it's a three-step process which involves a liquid or solution which is atomized into droplets, solidified by contact with a cold fluid, then sublimate at low temperature and pressure. So we can use this different drying technique. It's possible to functionalize the nanoparticles because, of course, if less OH groups are available, so it will limit the aggregation. Physical coating of the nanoparticle, or another option that has not been really explored in the literature is the use of never dry nanoparticles, which is called liquid feeding, meaning that the dispersion of nanocrystals can be directly inserted into the extruder and extrude with the polymer. I will show you some examples. So the first one is the physical coating of the nanoparticles. In this case, maltodextrin was used as a capping agent. Maltodextrin is a short molecular weight starch. And what was expected here is that this small molecule can have strong interactions with the surface of cellulose and avoid the aggregation. And then, because it's a low molecular weight starch, it can be just removed by rinsing the dispersion. So you have here the aspect of the dispersion. So this one, A, corresponds to, sorry, we will start with B. B is a never dry CNF dispersion. At the beginning, after 1 hour, after 24 hours. The suspension is stable. For A, it corresponds to oven dry and redispersed CNF. We clearly see the sedimentation due to the agglomeration of nanofibrils during drying. And here you have dispersions that have been obtained from never dry CNFs that have been mixed with maltodextrin in different ratios, dry, and then rinse to remove the maltodextrin, and it is rinsed with hot water and then redispersed. You can see that the stability is not so good as the never dry dispersion on nanofibrils, but much better than without maltodextrin. You can see here the aspect of these nanofibrils. Never dry cellulose nanofibrils, so we have these very thin nanofibrils. Oven dry cellulose nanofibrils, aggregates. And here, two nanofibrils that have been oven dry, but with maltodextrin that limit the aggregation of the nanofibrils. So this is another example in which is a little bit similar, but instead of using maltodextrin, NaCl, so it's sodium chloride, yes, sodium chloride has been used to avoid the aggregation of the nanofibrils. In fact, this process is used by Celluforce, a Canadian company, and they can solve cellulose nanofibrils or nanocrystals in the form of powder in the solid state because they had this salt. So I will not maybe go too into the detail, but when the CNF were dry and then redispersed in water, we observe this sedimentation for different pH. And when adding salt, so I don't remember exactly the difference between these two, we can see that the sedimentation is limited. And this is because of the insertion of the Na plus and Cl minus, sorry, ions. We have ion-dipole interaction between the nanofibrillate cellulose and NaCl salt, which act as a hydrogen bond blocker. This is another example in which, so the strategy is the same, but in this case, carboxymethyl cellulose was used as a capping agent. So it prevents the aggregation. Again, I will not detail everything, but you have here the absorbed amount of carboxymethyl cellulose as a function of the carboxymethyl cellulose that has been added to the dispersion. It was performed at 2 temperatures, and we have these different elements here at high temperature, room temperature, and with different amount of carboxymethyl cellulose. So globally, we have an improvement in the dispersion. Now the dispersion in polymer melt. What is possible? In situ polymerization, meaning that the nanofibrils or the nanocrystals are mixed with a monomer, and then in situ, the polymer can be polymerized. we should have a better dispersion in a liquid than in a polymer melt. Functionalization of the nanoparticles, again, physical coating of the nanoparticles with a surfactant, polymer, a copolymer, or a master batch. You know what is a master batch? Maybe I can define. Master batch consists in preparing a composite, usually by casting evaporation, with a high amount of filler. It's usually 30 or 40%. And so we have a homogeneous dispersion of the filler in the polymer, and this master batch can be extruded with virgin polymer pellets to dilute the filler, to reach, for example, 10% or 5%, so depending on the amount of master batch and virgin pellets which are used. Okay, so the filler is dispersed in the matrix first at a high amount, and then it is diluted. I will show you an example in which cellulose nanocrystals have been grafted with aliphatic chains with different lengths. So it was an esterification process, and these nanoparticles have been extruded with low-density polyethylene. So you can see the aspect of the low-density polyethylene here, and this is this polymer that was extruded with 10% of whiskers or nanocrystals, and which were not modified, and you can see several dots, brown dots, and so this reveals, of course, some aggregation of the nanoparticles, but also some thermal degradation, okay, because of the change in the color. And here you have the same polymer that was extruded with 10% of modified nanocrystals using the longer chain, and you can see that the aspect is completely different. Now, what about the mechanical properties? You have here the tensile strength, modulus, elongation at break, as a function of CNC content for the different samples, with and without modification, except here, for this curve, there is no change. We have a better dispersion of the nanocrystals in polyethylene after modification, of course, but no improvement in the mechanical properties. What is the reason for this? Do we have any idea? We block the OH groups. The formation of the percolating network is no more possible, meaning that even if the dispersion is improved, there is no improvement in the mechanical properties. These are some other examples in which compatibilization was performed, in this case using imidazolium PLLA surfactant, so with a positive charge here that can interact with the sulfate groups from the surface of the nanocrystals, and this part, which is PLA, because the matrix that was used was PLA. Another example is a diblock copolymer of polyethylene glycol that can interact with the OH group from the surface of the nanocrystals, and PLA that will interact with the matrix. We can see the impact on this SEM micrograph. This is a pure PLA. PLA with 5% cellulose nanocrystals. You can see here a big aggregate and no interactions between the two elements, between the matrix and the reinforcement. And here with 10% nanocrystals, using these two compatibilizing strategies. We cannot see aggregates, but in SEM, we cannot see individual nanocrystals. So this is an indication that there is no aggregate. This is another example in which polycaprolactone chains have been grafted on the surface of cellulose nanocrystals using a grafting from approach. And you see the impact. So the matrix that was used was polycaprolactone, 8% nanocrystals. This is AFM. We can see a bigger aggregate when the nanocrystals were graphed with polycaprolactone, no aggregate. So this is an interesting thing that has been developed by my colleague Steve Eichhorn in Exeter, in UK. He proposed a combination of Raman imaging with image analysis as a powerful and useful tool to quantify the degree of mixing of cellulose nanocrystals, in this case, with melt compound high-density polyethylene. So a compatibilizer was used, so it's a maleic anhydride polyethylene. And these are the Raman spectra for CNC, for high-density polyethylene, and for the mixture of these two polymers. And so he reports this image, this chemical image, which were extracted from Raman image, for freeze-dry nanocrystals, which are here, 2.5%, 5%, and spray-dry nanoparticles, 2.5 and 5%. So, in red, we can see the matrix. It's high-density polyethylene. In green, it corresponds to cellulose nanocrystals, meaning that the green part here consists of aggregate nanocrystals. And in blue, it is a mixture of high-density polyethylene and cellulose nanocrystals. So what we can conclude here is that in this case, 2.5% freeze-dry, the dispersion was better. So it was not perfect, but it was better. Now regarding the thermal stability of cellulose nanomaterials, so it was shown that the thermal stability of cellulose nanocrystals decrease when the acid hydrolysis treatment is performed with sulfuric acid. And remember that usually sulfuric acid is used because a good or stable suspension results from this process because of the grafting of sulfate groups. But in this study, TGA, thermogravimetric analysis, was performed for nanocrystals that have been extracted from using sulfuric acid hydrolysis, with different strengths, different concentration. And it was shown that as the severity of the acid hydrolysis treatment increases, the thermal stability decreases. What was observed also is that it was a two-step degradation process. A low temperature process that corresponds to the amorphous or the degradation of amorphous or highly sulfated region, and a high temperature process which is corresponding to the anterior or the less sulfated region. So, what are the possibilities to avoid this early thermal degradation? Hydrochloric acid can be used, but the problem is that the suspension is not stable. But it avoids the degradation. You can see cellulose nanocrystals that were obtained from sulfuric acid that were hit during 30 seconds at 200 degrees, it's brown. With hydrochloric acid, it's white. It's not degraded. And we can see also this from a TGA experiment. Phosphoric acid was proposed because we have a better stability of the suspension compared to hydrochloric acid, and the degradation is not as is similar to that with hydrochloric acid. So also regarding the thermal stability of cellulose nanomaterials, cellulose nanocrystals have been coated through chemical grafting or physical wrapping. In this case, it's a physical wrapping because a quaternary salt was used with a positive charge that can interact with the negative sulfate groups. And of course, the presence of this surfactant decreases the hydrophilicity of the nanocrystals. You can see here, this is the contact angle as a function of time for CNC, and for CNC that were coated with this surfactant. The contact angle of water increased, so meaning that the material is more hydrophobic. At the same time, we can see from TGA experiment that after modification, the thermal stability is improved because of the coating of the surface of nanocrystals and then the coating of the sulfate groups. These nanocrystals have been used for extrusion with polypropylene. You can see here the aspect of pure polypropylene. Polypropylene that was extruded with 1% cellulose nanocrystals. You can see the thermal degradation of the material because it becomes yellow or brown. And when it was extruded with 1 up to 10% of coat nanocrystals, you can see that there is no thermal degradation. The mechanical properties was investigated. So this is the storage modulus as a function of temperature for neat polypropylene and for polypropylene reinforced with unmodified or modified nanocrystals. So the reinforcing effect is weak. It is weak because polypropylene is a semi-crystalline polymer. So meaning that the crystalline domains give some stiffness to the rubbery material. And in addition, and it is quite often the case, when you check the degree of crystallinity of the material, this is for the pure polypropylene, polypropylene that has been extruded. This is the melting point, degree of crystallinity. Polypropylene with 3% CNC, or from 1 to 10% CNC. You can see that adding the nanocrystals increase the degree of crystallinity of the matrix, which is well known. We'll show later. But now the question, this improvement of the modulus is directly due to the reinforcing effect of the nanocrystals or to the increase in the crystallinity? We don't know. So this is another example in which different PLA, two different PLA which are here, have been grafted with, cellulose nanocrystals have been grafted with PLA, also with a grafting foam approach. And you can see the samples that have been obtained. So this is for unmodified nanocrystals, 2%, 4% to 8%. You can see the thermal degradation. And after modification, we can see that the degradation is much less. So this is another example regarding the thermal stability. And so it's a very long history because it's something that I have started to see. It was published 10 years ago. But anyway, we tried to investigate this with a master student maybe 30 years ago. And we found something which was strange, but we didn't go later, and we got back to this. So the thing is that we use polyethylene oxide. The polyethylene oxide is a water-soluble polymer. It was dissolved in water at room temperature, 1.25%, and then cellulose nanocrystals were added in different content in this polymer solution. So addition of water was performed to reach a final pH concentration of 1%, and you can determine the concentration of cellulose nanocrystals. The viscosity of the dispersion was determined. So we cannot see too much the thing here, but we can see here. This is for two different kinds of nanocrystals. Nanocrystals extracted from Capim dorado or from cotton. with different molecular weight of polyethylene oxide. What you can see is that when adding cellulose nanocrystals, we observe first a decrease in the viscosity, which was not expected. You add nanoparticles to the polymer solution and the viscosity decreases. And then it increases. So for both types of nanocrystals, and you can see that the minimum viscosity decreases when decreasing the molecular weight of polyethylene oxide. So what happened? Most probably, there is a good affinity, of course, between polyethylene oxide and the surface of cellulose nanocrystals. When adding the cellulose nanocrystals, the PO chains tend to go to the surface of the nanocrystals, meaning that there are less polyethylene oxide chain in the solution. It results in a decrease in the viscosity. And then, when the surface of the nanocrystals is completely covered, of course, we have an increase in the viscosity of the suspension. So anyway, we check this, we don't know exactly what happened, and something like 20 years later, we think, so why not using this for extrusion? Because when considering the cellulose nanocrystals, our nanocrystals mix with polyethylene oxide, you can see that there is an increase in the thermal stability because of the coating of the nanocrystals. And when using, again, low-density polyethylene, pure polyethylene, or with 3% or 6% nanocrystals, we still have this thermal degradation that can be clearly observed. But when using modified nanocrystals, we don't have this thermal degradation. Now, regarding the mechanical properties, so you remember with chemical modification, no improvement. Here again, no improvement. And if we compare with the model of Alpine Cardoz we mentioned previously, which is also it's here, it's not so bad. So it means that we have no interaction between the nanocrystals. And there is no interaction, so no formation of a percolating network, because, of course, of the coating of nanocrystals with polyethylene oxide chain. And again, like for polypropylene previously, we observe an increase in the crystallinity of the matrix. I will discuss a little bit about this. So you probably know that during the crystallization of polymers, there are two steps. The first step is the nucleation or germination, and the second step is the growth of the crystal. And usually, when adding solid nanoparticle or nanoparticles in a polymer, these particles act as a nucleating agent, meaning that the nucleation or the formation of crystals is promoted, but usually the growth is limited. I will show you an example, so in which, I have to remember, yes, this is for cellulose nanocrystals, this is for cellulose nanofibril, contact angle as a function of time. This is for unmodified nanoparticles, and here, nanoparticles that have been modified with an isocyanate, following two different strategies, two different methods. Of course, after modification, the material is more hydrophobic. What is interesting to see also here is that you can see that from cellulose nanocrystals, the contact angle is, let's say, around 40, maybe 45 degrees. For cellulose nanofibril, it is around 60 degrees. Nanofibrils are more hydrophobic than cellulose nanocrystals. Remember that cellulose nanocrystals consist of pure cellulose. Nanofibrils contain few percent of lignin and hemicellulose. So it means that these nanofibrils are more hydrophobic. Now we check the crystallization. I will not detail everything, but an isothermal crystallization was performed at 46 degrees. And we observe the crystallization So for the pure matrix, and for the matrix containing, I don't remember, it was maybe 12% cellulose nanocrystals and 12% cellulose nanofibrils. This is the relative crystallinity as a function of time for the matrix and for the composite. You can see that the crystallization is much faster. And it was observed also that the activation energy for crystallization was lower for the composites compared to the neat PLA matrix. We can observe this germination using a polarized optical microscopy. This is a polarized optical microscopy after 100 seconds of isothermal crystallization. So this is for PEO at 53 degrees, so the melting point is around 60 degrees. The pure matrix and with 10% nanocrystals. We can see that the crystals are smaller, but there are more because nucleation was easier. This is similar with PLA, pure PLA, so crystallization was performed at 125 degrees Celsius. Pure PLA, we have the formation of spherulites. You can see few spherulites, but the size is big. When adding 1% nanocrystals, or 1% modified nanocrystals, using a silane in this case, you can see that the crystals are much smaller, but there are more crystals, meaning that germination is favorable. This is another photo that I like very much, this one. This is a cellulose nanocrystal film, and it was immersed in a isopolypropylene melt, and crystallization was performed, so at 136 degrees. And you can see here polypropylene crystallization in the polymer in bulk, in the polymer melt, and at the surface of the cellulose nanocrystal film, we have this transcrystallization that can be observed. So we have seen the drying of the nanoparticles that can be a drawback, the dispersion in the polymer matrix, the thermal stability, structural integrity can also be a problem. During injection molding or during extrusion, high shear rates are involved, meaning that it's possible to break the nanocrystals. And this was observed. This is cellulose nanocrystals before extrusion. They were extracted from RAMI and after extrusion. In fact, these nanocrystals were extruded with polyethylene oxide, and so it's quite easy to recover the nanocrystals after extrusion because polyethylene oxide is a water-soluble polymer, meaning that the extrude composite can be dissolved in water and the nanocrystal can be recovered. This is the length of the nanocrystals before, after extrusion. We can see that effectively the nanocrystals were broken. Initially, the average length was 200 nanometers. After extrusion, 122. But, and we can also observe a narrowing of the length distribution, becomes more monodispersed, just due to the fact that there is more efficient mechanical degradation of longer nanocrystals. The diameter also slightly decreased, meaning that globally the diminution in the aspect ratio was limited. This is another example in which different processing techniques have been used. It was with polyvinyl acetate as the matrix, solvent casting, no shear rate is involved, roller blade mixing, so higher shear rate, and twin screw extrusion, further higher shear rate. And we can see the length for the parent CNC, solvent casting in red, in green, roller blade mixing, and for extrusion, we have a strong reduction in the length of the nanocrystals. Another problem, and of course, this reduction in the length of the nanocrystal can be a problem for percolation. Another problem for percolation can be the orientation of cellulose nanocrystals. So strong shear rate are applied during extrusion or injection molding, meaning that we can have some orientation of the nanorods in the direction of the flow. And so to observe this orientation, we use, this was a PhD from Kerala, we use a small angle X-ray scattering, for nanocomposite consisting of low density of polyethylene and cellulose nanocrystals. They were compatibilized using this 3-block copolymer. And so what we can observe is an azeotropic phase of the signal, which is an indication of some orientation of the nanocrystals. We also, so this time it was a Brazilian PhD student, we try also to evidence this orientation using a very specific technique, which is the 2D small amplitude oscillatory shear experiment. In fact, it is like dynamic mechanical analysis, except that in dynamic mechanical analysis, you know that a periodical or sinusoidal stress is applied to the material, for example, in tension, and the deformation is measured. In this case, the deformation was applied in 2 directions, perpendicular direction and also in rotation. And so for this experiment, we use nanocrystals, and for the matrix, it was PBAT, polybutyrate adipaterephthalate. So it's this polymer, it's a biodegradable copolymer. And what we obtain from this experiment is the evolution of the perpendicular stress and the angular stress as a function of the strain. What we should obtain is 2 circles, if there is no orientation. But we can see in this case that it's not a perfect circle. The reason is that during extrusion, and then we use injection, we have some orientation of the macromolecule. This is for the pure matrix. We have some orientation of the macromolecule, and this is the reason why we don't have let's say, a perfect signal. Then the experiment was performed with 0.9, 1.8, 3.6% cellulose nanocrystals. We can see that by increasing the CNC content, we have a bigger difference between the 2 stresses. So meaning that we have some orientation. And what we try is to condition the material at high temperature, 170 degrees, so it's higher than the melting point of PBAT, during 30 minutes, and so we are sure that no degradation occurs, and we perform again the experiment. Not so much difference. What we expect with this thermal treatment is maybe that we can destroy the orientation of the nanocrystals and maybe recover the formation of the percolated network. But we didn't think too much because the polymer melt is highly viscous. But there are some differences. This is a creep experiment. So creep experiment is a mechanical test in which constant stress is applied to the material. You can imagine that you attach a weight and you evaluate the variation of the elongation of the material or the deformation of the material as a function of time. So this was done here at high temperature above the melting point of the polymer for the pure matrix. So this is the strain as a function of time. For the pure matrix, we have this linear evolution. This linear evolution reveals a liquid-like behavior, which is normal because we are considering a polymer melt. If we consider a perfectly elastic material, we should have a step and then a stabilization. Now for the composite, what we observe is this. So maybe this one before conditioning, we have this behavior. You can see that we have an evolution and then a kind of stabilization. So this is typical of a solid viscoelastic behavior. And after conditioning at 130 degrees for 30 minutes, we still have a solid viscoelastic behavior, but it's different. Meaning that during this heat treatment, something happened. We don't know why, but something happened. So, I think it's time to conclude. So mail processing is a relevant approach to elaborate bionanocomposite. It is challenging to implement, but it is a step towards a large-scale use of this material. We have seen the different challenges which are associated to mail processing, aggregation of the nanoparticles upon drying, homogeneous dispersion within the polymer melt, low thermal stability of cellulose nanomaterials, mainly nanocrystals, structural integrity of the nanoparticle, orientation of the nanoparticle. And so what I try to show you is that some strategies have been proposed to overcome these issues, but none of them has produced satisfactory results. The mechanical properties are far from expectation and due to difficulties in forming a percolating nanoparticle network. Compared to the first study that I show you from that was published in 1995, nobody reached the same reinforcement effect. So, this extrusion can be good, but you see the problem. You have to avoid the aggregation, you have to promote the dispersion, so it means that for this you need to block the OH group from the surface, but for this, of course, you limit the interaction between the nanoparticles. What could be done? Maybe you have an idea. Tell me if you have an idea. Is to have chemical or product that block the OH groups during the extrusion and that can be removed easily after extrusion by a thermal treatment, by radiation, or I don't know. It will be good. So if you have an idea, you can email me. Thank you very much.
The session is open for questions.
Dispersion aspects, when different matrices have different levels of interaction with cellulose particles,
Sorry?
Different matrices have different levels of interaction with the matrices. So, what are your generalization? What are your observations in generalization? Polar interactions primarily control it.
I mentioned at the beginning, right? But you are not.
That could be, sir. I'm sorry for that. I'm sorry for that.
No. When you consider polyethylene oxide or starch as a matrix, so it's a polar matrix, you can think that it's not necessary to have any compatibilization because there is good interaction with cellulose, but usually grafting of polyethylene glycol is performed because you preserve the hydrophilic character of the nanocrystals that can interact with the matrix, but because of this change with a graft at the surface, it limits the aggregation. Because during extrusion, even if both the matrix and the reinforcement are polar, of course, because of the shear rate, you will have some aggregation.
Sir, for high density polyethylene composites now, we use usually melt mixing technique. Are there any alternative techniques for the preparation of such composites? For
Alternative technique
high density,
high density polyethylene?
yeah, for high density polyethylene based composites and all, usually we use as melt mixing technique for the preparation of such systems. Are there any alternative techniques for the preparation of such composites?
I'm sorry, I'm not sure. Can you come closer because it's difficult to hear you. Because the air conditioning is.
Sir, for high density polyethylene based composite systems, we use usually melt mixing techniques for the preparation of such composites. Are there any alternative methods for the preparation of such systems?
An alternative method to what? Sorry, I don't understand.
She makes high density HDPE.
Yes?
So this, she wants to develop
I prepared it using melt mixing technique.
seeds for melt mixing. Melt.
Yeah, okay.
Do you propose any better method for that?
With high density polyethylene. Yes, with high density polyethylene.
Yeah.
The problem with high density polyethylene is that there are some solvents, but I think they are not very friendly. So meaning that melt processing is the best processing technique. It is the best one, but of course there are many drawbacks. I know. Another option I have to remember. I think I have already seen that polyethylene can be available as a latex. It's maybe not easy to find, but I think it can be available as a latex. So in this case, the processing is much more easier. But also it depends on the size of the latex particle.
Okay, thank you.
I have a doubt, like slide number 24.
24. The equipment, you mean it was for the integrity of the nanoparticles, the decrease in the length, no?
No, so it's an image.
It's an image? Yes. But it is an image of nanocrystals before and after extrusion. Yeah. Okay. Ah, it's a 24, yeah, okay. Yeah, okay. Yes.
That image, how did you take it?
In fact, it's a microscopy, optical microscopy.
Optical microscopy?
Yes, but it's polarized optical microscopy. It's necessary to see this spherolite. In fact, this is classically used to see the crystallization of polymers in the form of spherolite. Because when you have spherolite, you have this typical pattern, which is called the Maltese cross. Maltese cross. Maltese, you know, Maltese cross. Maltese, so it's a very long story. Maltese, so it's come from Malt, the island. And the Maltese cross, it was in several centuries ago, and their symbol was this kind of cross. And so it is called Maltese cross.
It's a polarized light that is passing.
Polarized light, yes, and the reason for using polarized light is just to see this Maltese cross, which is representative of radial crystallization, which is the case for spherolites.
Sir, is there any option to find out strain-induced crystallization through any imaging technique?
So, you mean another imaging technique?
Yes.
No.
Especially strain-induced crystallization, like through some method.
For strain-induced crystallization, usually what is done is that we record the X-ray diffraction pattern during the test. And so we can see the emergence of crystallization peak.
So XRD coupled with tensile.
Exactly. But in this case, yes, yes. After that, maybe you can have an idea, but it's not so clear as here. If you perform DSC experiments on this sample and on this sample, which difference did you expect? You can see the difference is that here you have big crystals, here you have small crystals.
So maybe crystallization peak difference.
The temperature of melting, of the melting point. because the melting point is directly linked to the size of the crystal. When you have big crystals, the melting point is higher. When it's a small crystal, the melting point is lower. Now you can also check the degree of crystallinity, but it will not give too much information because you can have few big crystals and many small crystals, and you can have the same degree of crystallinity.
Thank you, sir. Any more questions? Sir, this is a general question. So we have seen both wet method and melt method. So one is like non-economic, other is economic, but one has got more good properties. The other is kind of backwards in case of properties. So according to your expertise, how practical is biocomposites right now in the market field and industry field than in a laboratory field?
In fact, of course, it's difficult to obtain the same properties when using the melt method compared to the wet method. Wet method can be a good option for paint, for example, but it's very specific. Now, if we consider that melt processing is more economic, we can think that, okay, when using, for example, 5% cellulose nanocrystals, we know that the mechanical properties will be lower than when using 5% cellulose nanocrystals by casting evaporation. But if the process has a lower cost, maybe we can add 10% instead of 5% for solvent casting. So we can compensate by adding more nanocrystals to have the same mechanical properties. It can be an option.
So one more question. Basically, biocomposites are biodegradable and biocompatible. Have you considered recycle,
It depends, because I show many examples with
which are not biodegradable? Yes, yes. Sir, I'm coming to that. Have you considered about recycling of biocomposites?
Yes, I think it's important. If the matrix is not biodegradable, of course, but I think that even for biodegradable materials, so it can be, because biodegradable so means that maybe for packaging, if it is in the nature, it can degrade by itself. If you keep the material at home, it will not degrade. And so if it can be recycled, so it can be good, yes.
So up to what extent the recyclability is,
Yes.
like up to what extent the recyclability is attained right now?
After what extent?
The recyclability of this particular.
It depends on the polymer, it depends on the recycling way. You know that there are two strategies for recycling. Mechanical recycling, that consists in grounding the product and then it can be extruded, for example, or chemical recycling. Chemical recycling, you can perform it as much as you want. The problem is that, of course, it is more expensive. But there is no limitation for chemical recycling.
Thank you, sir.
Sir, in the case of creep test, the temperature you mentioned 170 in that composite.
The creep test, yes.
Last slide, I think.
Zero.
Yeah. In the case of composite, how can we fix the temperature? Means how we will find that 170 degrees Celsius?
I'm sorry, what? Yes, come closer.
The temperature part is there.
Yes, the temperature 170 degrees.
How can we determine which temperature we have to do the creep test?
In fact, we use this temperature because we want to see what happened in the melt, because we are interested in the melt processing. But this experiment can be performed at any temperature. I don't know if it is a question, but no.
It should be some percentage of melting point, right?
Here it is above the melting point.
It's close to melting point.
Yes, the melting point of PBAT is around 120 degrees. And so here we are considering a polymer melt. And you can see that, by the way, the force which is applied is very low
Okay.
because it's a polymer melt. I don't know if it is a question. No.
Yeah. I'm feeling it should be around 50% of the melting point. Then it should be. It is almost same like a tensile testing at high temperature.
No, it's not a tensile testing. In fact, for mechanical test, you have two different type of test. Static test and dynamic test. So dynamic test is dynamic mechanical analysis, meaning that a sinusoidal stress is applied. Static test, it means that one mechanical parameter is constant. In the case of creep, it's a stress. A constant stress is applied to the material and you can follow the evolution of the deformation. Stress relaxation, it's a test in which the deformation is constant, so you stretch the material, for example, and you keep the deformation, and you follow the evolution of the stress, which is necessary to keep this deformation as a function of time. Tensile test is also a static test. So what is the mechanical parameter which is constant? I use the question to all of you. Which mechanical parameter? Mechanical, I don't mean the temperature and so on. Mechanical parameter is constant during a tensile test.
Tensile strength.
Yes, in fact, the elongation rate, you extend at 10 millimeter, for example, per minute. This is a parameter which is constant. Okay? And so in creep test, the stress applied to the material is constant.
But the temperature is crucial here, right?
No, you can choose the temperature you want. You can perform the test at any temperature. In this case, it was above the melting point because we want to know what happened during melt processing. But it can be, of course, below the melting point, below the TG, at any temperature.
Yeah. Thank you.
Okay.
Any more questions? So if there are no questions, let me take this opportunity to thank Professor Allen. So let's give him a big round of applause.